Welcome to today's analog microelectronic circuits class. And this particular lecture will be dedicating to solve the tutorial questions from Unit 2, that is BJT. So I have given you a set of questions yesterday. So we'll start from our very first question. The first question. The voltage divider biasing circuit was given, and you were asked to find the operating point of the NPN transistor. Let me redraw the question here. So this is 2.7K. This is 3.9K. This is 24 volts. This is 47K. This is 18K. And given that the beta value is 75. Right. So this is a question given. So you are asked to find the operating point of the NPN transistor. So Huma, are you there? So I'll be calling your names quickly and you respond,
Yes, sir.
and this I'll consider as your attendance also. So Huma, can you tell me how to start solve? So what do you mean by operating point of the NPN transistor?
I think whether it is an active region.
Yeah, so what decides whether the transistor is in active region or saturation region or cutoff?
VBE should be great if it's greater than 0.7.
Yeah, so for a transistor to be in any of the regions, the biasing is important. The emitter-based
that
junction
should be
biasing and
forward.
collector-based junction biasing, right?
Yeah,
So that
yeah.
biasing should be there. And
Yes.
what we generally call as operating point is actually the value of IC and VCE. These two are called as the operating point value. So when I say IC, IB and IE values are known, or we can evaluate those two also, right? So for the emitter based junction should be forward bias. That means your VB should be minimum 0.7. So what we are asked to find is the value of IC and VCE. Now, can you tell me how to start this? No, I'll check with Jayaditya. Thank you, Huma. Jayaditya.
Yes, sir.
Yeah. So can you tell me, Jayaditya, how to start this?
We can find out the potential at the base.
So how to do that?
You can write the KVA voltage bias.
Yeah, this is a voltage divider bias.
18 by 47 plus 18.
Okay, that is?
That will give you the voltage at the base.
Okay. Now you meant to say that if you have a connection like this, you can say, so if this is 47K and this is 18K and if this is 24 volts, you can find this voltage, right?
Yes, sir. Yeah.
As 24 into 18 by 18 plus 47.
Yes, sir.
But this is true when there is no current flowing here. And this is open right here.
Okay, like.
But in our
sorry,
case, there is a current. That is your base current. So what will we do for such?
You can do this. Consider the potential at base as VB. And write the KVL by across the thing. Since it's I'm assuming it's silicon. It's VB minus 0.7.
That is okay. Now my question is, what I am telling is, what is this VB, or how will I write the VB voltage here? VB is actually the base voltage, right? So since there is a current, I cannot directly apply this potential voltage divider biasing rule.
Yeah.
So what I should do for this? Yes, Jayatidya. Okay, let me check with Jeevita. Jeevita?
Yes, sir.
Yes, Jeevita.
So
Again,
we can find Thevenin's voltage,
Yes, very good. So we have to evaluate. I think I have done that, right? Yes. So whenever you have this kind of circuit in MOSFET, so Jayaditya, in the case of MOSFET, what you are telling is true because MOSFET there is no gate current. Since there is a base current, I have to convert this into its Thevenin equivalent. So that means we have to find what is VTH and RTH.
Okay, yeah, sorry.
Yeah, yeah. I hope you understand that. That's all right. So Jeevita, go ahead.
Yes, I got it. I got it.
So, uh, 24 Thevenin voltage can 24 into 18K
Hmm.
divided by 18 plus 47.
Very good. Thank you, Jeevita. So Jessica,
Yes,
what is this? Yeah, what is this VTH value? Can you calculate and tell me?
yes. Uh, so
So
six
Abhirami, you
point
can calculate the RTH value. I'll ask you now. Yeah, 6 point.
646.
Very good. Yes, that is VTH. Right. Thank you, Jessica. Abhirami,
Sir, RTH is 13.02.
that is 47K parallel to 18K, right?
Yeah.
Okay. Thank you, Abhirami. Anushka,
Yes, sir.
what is next?
Um, we can find IB.
Yeah, so to do that, should I draw one more circuit by including VTH and RTH?
Yes, sir. With the new found VTH and RTH, we should.
Okay, very good. So this is my VTH. Here I have RTH. Then I will place the transistor here. At here I have 2.7K and here I have 3.9K. This is 24 and this is 13.02 and this is 6.64. All right, so Anushka, can you help me to evaluate IB? How will you do evaluate IB?
3.9K minus
Mm.
IB into 13.02K.
Oh, that means you are considering a loop like this.
Yes, sir.
Okay, now if I take a loop like that, what is this voltage?
Okay, we should. Um, IB is going like towards.
Yeah, so the direction, if you mark the direction of current, this is IB, this is IC, and this is IE, right?
Yeah.
Yeah.
Yes, sir.
So Anushka, thank you for your response. So make a point here. This is to everyone. So whenever you are starting with any BJT based problem, so if you can see that the transistor, there is a chance that transistor will be an active region, or you can go ahead with the assumption that if sufficient potentials are connected to collector and base to make it an active region, you can go ahead with an assumption, assuming that the transistor is an active region, you can always go with the base loop because when transistor is in active region, you have VB voltage of 0.7. Your VB voltage is 0.7. Uh, uh, just a minute. Yeah. All right. So the important point to note here is, so you have to always go ahead. Am I audible?
Yes, sir, you're audible.
Yeah. So we have to go ahead with the base loop. Why base loop? Because if the transistor is an active region, you can take that your VBE active is 0.7. Right. Anushka, is that clear now?
Yes, sir.
Yeah, so you cannot go with this loop, the green what I have marked here, because this voltage will be unknown. VCB voltage will be unknown.
Okay. Yes, sir. Like
Right.
now we
Yeah.
know 0.7. Up we didn't know about that.
Yeah, yes, very good. Correct. Okay, thank you, Anushka. Karan.
Yes, sir.
Yeah. So can you tell me how to proceed now?
Uh, I don't know, sir.
What happened, Karan?
I I don't know, sir.
Okay. Okay. My question is what you do not know.
Like the next step.
The next step, okay, I'll give you a hint. The next step is to evaluate one of the currents. So as I just told now, since in active region my base emitter voltage is known, since it is a known value, I can take this as 0.7. Now, which current can be easily obtained?
IB.
IB. Okay. Why did you tell IB? Yeah, IB is a current flowing here, but now this is IE. So can you tell me, can you form a loop here and tell me how to evaluate IB? Okay, Karen, you just listen. I'll be explaining. Okay.
Okay, sir.
Okay, no problem. Carmagil?
Yes, sir.
Yeah, Carmagil, can you tell me how to write the loop equation here?
6.64 minus
Yeah, so it is
13.02 K into IB.
Yeah, so this is minus plus. Current is flowing in this direction, so plus minus. Again plus minus, and this is plus minus. I hope this is clear. So minus to plus, it is 6.64 minus 13.02 K into IB. Yes, go ahead.
Minus
Carmagil.
0.7
Minus 0.7.
minus 1 plus beta into IB into
2.7 K, right? So 2.7 K into
1
beta
plus
plus 1 into IB. Why?
IB.
Because we know that IE is equal to IB into beta plus 1. So the note what I was telling is start with the base loop. Thank you, Karmali. Yeah. So Kartikeya, this is equal to 0. Yeah.
Yes, sir.
Kartikeya, so in this only unknown is IB, beta is given as 75. So can you calculate and tell me what is the IB value?
Yes, sir. This one.
Yeah. Kaushik, I will be asking you what is the IC and IE values. You can calculate both IC and IB. Oh, okay. For that you need IB, right? Okay. Kartikeya?
Doing it, sir. This one.
Okay, okay. So it is 6.64 minus 0.7 divided by 13.02 K plus 76 into 2.7 K.
So this is 2722.
Yeah, 27. Yeah, very good. IB is 27.2 microns. Very good, Kartikeya. Kaushik, can you tell me what is the IC and IE values? Kaushik?
Yes, sir. So
Yeah.
IC will be beta into IB.
IC is?
Beta into IB.
Yes.
And that will be 2040 micro. 2040 microamps.
So 2.04 milliamps, and IE is?
IE is 1 plus beta into same thing. So
Yeah. So
2.052.
2.068, I think I'll get. Okay. All right. Thank you, Kaushik. Kirtana. Kirtana. Kirtana, are you there? Yes, Kirtana. Kirtana, my question is, so we have taken base loop and we evaluated IB, and through IB we evaluated the other currents. Now, how will you evaluate VCE?
Sir, we will take that voltage from 24 volts to the ground. We'll
Oh,
take
this
a
loop we'll take. Yes. So, okay. So, can you tell me what the equation there? What equation I can write?
24 minus
Hmm.
3.9 IC
Okay.
minus VCE
Okay.
minus 2.7 IE is equal to 0.
2.7 K into IE is equal to 0. In this, both IC and IE are known, so you can find VCE, right? Thank you, Kirtana. Kirti, B and C, are you there?
Yes, sir.
Oh, Kirti, yeah. Kirti, can you tell me what is VCE?
Sir, is it 10.5 volts?
Yeah, it is 10.45 volts. Very good. Very good, Kirti. Yeah, so this is the operating point of the transistor, NPN transistor. So we evaluated. So by this exercise, we evaluated all the currents and all the voltages, right? Okay, let us find out VB also. So when I say VCE, I know what is VC voltage, what is VE voltage. Now let me find VB also. So can you tell me what is VB? I'll check with Keshvi. Keshvi, are you there?
Yes, sir.
Yeah, Keshvi, what is VB voltage?
Sir, I'll calculate 1 minute.
Yes. Yes, so how will you calculate?
Sir, in that loop, 24 minus 47.
Where is 24 minus 47?
Sir, VBE.
VB, the node voltage VB.
So VTH minus IB into RTH.
Yes. What is that
VB.
value? Yeah.
Sir. Yes, sir.
What is the answer?
Yes, sir. So 6.286.
Yes, 6.286. Very good. Thank you, Keshvi. Yeah, so let us move to the next question, question number 2. Question number 2 is also same as question number 1. The difference is in place of NPN, you have a PNP transistor. So yes, let us try this because we haven't solved any PNP questions yet. So this is 18 volts, this is 2.2K, this is 150K, this is 470K, this is beta equals 60, and this is 3.3K. Again, the question is to determine the operating point of the PNP transistor. So we'll start with Kishan. Kishan?
Yes.
Yeah. So Kishan, I hope you followed the previous question.
Yes, sir.
Yeah. So what is the first step?
Yeah, finding the Thevenin voltage.
Very good. So can you tell me what is V Thevenin?
V Thevenin is 4.35 volts. I mean,
okay.
18 into 150K divided by 150K plus 470.
That means you did not follow the previous question.
Sorry. 18 into 470K divided by 150 plus.
Is that the VTH value?
Yes, sir, 1 second.
Kishan, look at here, no?
Yes.
How did we find? Yeah, right. Yeah, go. Sorry. Yeah.
Yes, 13.64.
Yes, 13.64. Very good.
Yes.
Thank you, Kishan. Krishna Pratik?
Yes, sir.
Yeah. So what is RTH value?
I got 113709.6 or
Yeah, that is
113 kilo ohms.
113.7 kilo. Very good. Thank you, Krishna Pradeep. Kriti? Kriti, are you there? Kriti?
Yes, sir.
Yeah. So, Kriti, can you tell me what is next step? Yeah, yeah, to find IB. What is IB value? All right. Laksh? Yeah. What is IB value, Laksh?
Yes, sir. 1 second.
Yeah.
I will calculate.
Sai Kiran, you can evaluate what is VCE. Soon after Laksh, I'll ask you. Sai Kiran, did you get IB, IC values?
Solving ICs, IBs.
Okay, okay, okay. All right, go ahead. You can solve it. I am just checking with others. Madhusudan?
Yes, sir.
Yeah. Did you get IB value?
Solving.
Okay, okay. Maheshwari?
Yes, sir.
Did you get the value?
14.7 microamps.
Okay, 14.76 microamps. With that, you can get IC and IE value. So I'll check with Rakshit. Rakshit?
Yes, sir. 1 second. I'm calculating.
Okay. Sai Kiran, you have any answer for IC or IE?
Solving.
Okay, okay, no problem. Yeah, IB is the same. Yeah, 14.76. Yes. All right, I'll check with others. Sai Kiran, no problem. Yeah. Yes, Rakshit. Sai Kiran, you can mute. Manikandan, ready with VCE value. After Rakshit, I'll come.
Sir, IC is equals to beta times IB.
Yes.
So it is 885.6
Micro,
microamps.
which is 0.88. I think I am getting 889 milliamps. You can check, and your IE is close to 0.9 milliamps. Correctly, the method is correct.
Yes.
Yeah, thank you. Manikandan?
Yes, sir. Just a second.
Yeah. Yeah.
Excuse me, sir.
Yeah. Yes.
Can I ask a doubt?
Kartigeya. Yes, Kartigeya.
Sir, like in this case, in PNP transistor, emitter-based junction is forward bias and collector-based junction is reverse bias, right? For
Should
active
be.
region.
Yes, should be.
But then for IB, how do we take the loop? Like upwards or this way?
Oh, yeah,
Down?
sorry, I didn't tell that, right? Yeah, the loop taken. Oh, very sorry for that. The loop taken is this, the base emitter loop.
Thank you, sir.
Yeah, yeah. Okay, sorry for not marking this. So your emitter current is flowing in IE, and this is IB, and this is IC. Right. So the loop, the green color loop is what we take to find this one. IB. Yes. So where are we? We are with Manikandan. Manikandan.
Is it 15.73?
No, it is VCE. So what happens here is you have to take this loop. Right. So it is
Yes, sir.
18 minus 2.2K into IE minus VEC you can write. Right. VEC minus 3.3k into IC equal to 0.
So
Yes.
can I answer?
Yes, please.
VC is minus 13.1 volt.
Yeah, you will get VEC as 13.08 or something.
VC
So
is
yes,
minus
yeah,
13.1.
VC is minus 13.08. All right. I hope Manikandan you got the answer. Or probably you would have missed something in the loop.
I'll check again, sir.
Yeah,
I
all
did
right.
the same equation, but maybe I'm doing some
Yeah, maybe
calculation
in the
error.
calculation error. All right.
Okay, sir.
Yeah, yeah. Thank you. Yeah. So that is the operating point of a second transistor. Through this, you can find the VB voltage also. I will ask who is there? Manjunath. Manjunath Prakash.
Yes, sir.
Yeah.
Yes, sir.
Can you tell me what is VB voltage?
So VB is 15.318.
15.
Hello.
Yeah, yeah. So 13.64 plus the drop across this, right?
Yeah, yes, sir.
I don't have the value. What is the value? 15.318.
318.
318. Okay. Let us check with others. Okay. 13.
Sorry, sir. Actually, I did wrong.
Yeah. This should be. This should not be right.
Yes, sir.
Okay. Let me
Wait,
check. Yeah. 18 minus. Your IE is equal to 0.9. So 0.9 milli into 2.2K. That is your VE minus 0.7. I think 15.32. It is correct only. Any other answers you got for
Yes, sir.
VB? Okay, let me check with Manjunath S. Manjunath S. Manjunath? Hello, Manjunath? Oh, okay. Yeah, so you can just calculate that and verify whether it is 15.32. If not, you just unmute and tell me again. Okay, so meanwhile, we go to next question. So before solving question number 3 and 4, let us solve question number 5 first. So question number 5 is again, okay, yeah, we haven't solved such questions yet. So question number 5 is, a circuit is given. A circuit is given. Right. This is given as 20 volts. This is 180 kilo. This is 6.8 kilo. This is 47 kilo. This is 2.2 kilo. And capacitors are connected here, where this is the input point. There is a capacitor connected here, and here also a capacitor is connected, and this is output point. Right. So the question asked is, yeah, beta is given for the transistor as 20. Sorry, 120 is the beta value. It is also given that R0 value for the transistor should be taken as 50K. Given that transistor is silicon, you are asked to find the voltages VB, VC. Also, you are supposed to find RE, Zin, Zout, and AV. All right. Yeah, this is a question. Okay. So, Manjunath, did you get the answer for the previous question? 15 points. The same answer you are getting. Is the same answer you are getting, Manjunath?
Okay.
I'm not able to hear you.
The same answer, sir.
Oh, okay. Okay. All right. Okay. So, Mihir Ji, are you there, Mihir? Mihir? Mihir, you are not there. Hello, Mihir. Okay. Mohan, are you there? Mohan?
Yes, sir.
Okay.
Yes, sir.
Yeah. Yes, Mohan. Just a second. Yeah, Mohan. So tell me, what is this question?
So amplifier only.
This is an amplifier. Okay. So this is to everyone. So we haven't solved a question like this in BJT yet, but we have solved a similar kind of question in MOSFET. So this question, we have to identify the type of amplifier. We have to do DC analysis first. That is to come with the to evaluate the operating point and thereby get the values of VB, Then we have to find the small signal parameters, and then we have to evaluate output impedance, input impedance, and voltage gain. Isn't it, Mohan?
Yes, sir.
Yeah. Now, can you tell me what type of amplifier is this?
It is like source degeneration.
Okay, so you said that it is source degeneration because you have seen a resistance at the emitter terminal, right?
Emitter terminal.
Emitter, yeah. So the very first thing is check where the input is given. So input is given to base, and from where output is taken. Output is taken from collector. So this should be a type of common emitter configuration. So it can be common emitter amplifier or common emitter with a source degeneration, and you identified now it as a common emitter with source degeneration, right?
Yes, sir.
Yeah, that is true, but since the capacitor is present, we will see what modification will happen it. So we will deal that soon after doing the DC analysis. Okay. Okay, Mohan. So I'll write here it as of now I'll write the CE. We will see whether it is common emitter with a degeneration or it is a simple common emitter. Okay. Okay. Now, why I am telling that I will see that after some time is because the amplifier configuration is determined by looking at the input and output, but at the same time we have to see the AC equivalent or the small signal equivalent of the circuit. Now, what happens? Okay, let me explain that here itself. So, what happens to these capacitors is all these capacitors, even in the case of MOSFET, we know that we have taken capacitors as short at the operating point, right? So your capacitor, these capacitors are to actually couple the signal to the circuit and to take the output from the circuit, and the capacitors will actually maintain the DC operating point. That is the role of the capacitor. Right. Now what happens is at the signal of interest, or when I provide an input signal here to the amplifier, I am assuming that all these capacitors will offer a very low reactance, or all these capacitors offer the capacitors will remain as short, right? So since the capacitors are remaining as short, can you tell me what is the what will be? So the question is again back to Mohan. Yeah. Now,
Yes,
if
sir.
the capacitors are acting as short, can you tell me what kind of amplifier is this?
Okay. So it is common emitter.
Yeah. Why common emitter? Since capacitor is short, for
Short.
AC equivalent, this will act as short. That means your emitter point is directly connected to ground, or the effect of the resistance will not come into picture. So this is a common emitter amplifier. Right. Is that clear, Mohan?
Yes, sir. Yes, sir.
Okay. Okay. Thank you, Mohan. Yeah. Okay. So who is next? Mauna?
Yes, sir.
Yeah, Mauna. Okay, Mauna, I hope you understand that this is a common emitter amplifier.
Yes, sir.
Okay, now can you tell me how to start with the calculations of VB and VC? Can I write the heading as DC analysis?
Yes, sir.
Yeah. Can you tell me what is the first thing to do?
So we can find VTH and RTH.
Yeah, so I'll just draw the DC equivalent. So what happens to DC is the capacitors will act as open, right? So I will draw the equivalent here. This is 20 volts. This is 180K. This is 6.8K. This is 47K. This is 2.2K. This will be the equivalent circuit. Okay, all right. So, Maunav.
Yes, sir.
Yeah, so what to do now?
So we can find VTH 20 into
Yeah,
47 by 180 plus 1, sir.
Yeah. So can you tell me what is the VTH and ITH values?
So VTH I got 4.141 and RTH I got 37.26 kilo.
Very good, very good, very good. Let me just draw it. Yeah, so the VTH value is 4.141 volts and RTH is
37.26 kilo.
269 kilo ohm. Yes, that is right. Now, now let me write these. Thank you, Manu. Yeah, this is 2.2. Now, Akram.
Yes, sir.
Yeah, Akram, tell me what is next step?
So, we'll find IB.
Very good. So, can you tell me what is IB?
So, 1 second.
Yeah, you calculate. I'll just write down the equation. It is 4.141 volts. So let me draw the symbol. See, this is IB, this is IE, and this is IC. Now IB is equal to 4.141 minus 0.7 because these two are the voltages. This is 0.7 divided by 37. So this what I'm writing now is a result of a KVL. So you have to write a KVL and that will give you IB value 37.2K plus 2.2K into beta plus 1 into IB, right? Yeah, so beta plus 1 is 121. I hope this will give the answer. So what is the answer, Akram? Hello, Akram.
4.137 micro.
Oh, okay.
Micro.
I think. Can you check again?
Yeah, 1 second.
Yeah, let me check with Subramanian. Subramanian?
So 11.335 microns.
Yeah, 11.339 microns. Yeah, probably you would have missed something in the calculation. Okay, no problem. Okay, thank you, Muthu. Subramanian. Now, who is next? Naman. Okay, let me tell one thing here. Why I'm finding IC, IB, and IE? If I want to evaluate VB and VC, I should know these currents, right? And Naman, what is the IC and IB values?
Sir,
IC and yeah.
I is 1.367 milli.
1.361 milli I got. Okay, IE.
So IE, 1 second. So is it 1.356?
No, IE should be more than IC, right?
Yeah, IE is 1.361.
It is 372 milliamps.
Oh, so I think I got different. I'll check.
Yeah, no problem. Yeah, you check again. Yeah, Namit.
Yes, sir. Yes, sir.
Yeah, Namit, I hope you got the answers. IC, IB, and IE.
Yes, sir.
Yeah, now can you tell me how to evaluate VB?
Sir, just a second, sir.
Yeah.
VB, sir, for evaluation of the VB, we'll apply the KVL, sir.
Yeah, so VB is this point, right? So what is VB voltage?
Sir, that's 4.141 volt minus 30, which like minus IB minus 0.7.
No, I'm asking you this voltage, VB. So VB is 4.141 minus this drop, right?
Yes, sir. Yes, sir. Yes, sir.
Yeah, so 4.141 minus this drop, or you can find, since I know IE into 2.2 plus 0.7. Either way you can write. So what is the VB value? You got any answer? Okay, I'll check with Namra. Namra?
Yes, sir.
Yeah, Namra, what is the VB you are getting?
So just a minute, I'm calculating.
All right, okay. Namit, you got answer?
So just a minute, sir, I'm calculating, sir.
Okay, no problem. Okay, let me check with others. Nandita?
Sir, I'm getting 2.2 kilo.
VB. Yeah, so VB is a voltage, right? So VB is 4.141 minus 37.2 K into 11.33 micro.
Yes, sir. Yes, sir.
Yeah.
I have to do so.
Can you recheck? Namra, you got an answer?
So is it 2.3?
No,
2.3?
it's not 2.3. Okay, Namit?
Sir, I am getting sir something in minus. I don't know, sir. I have done something wrong in the calculation, sir.
Oh no, it's very simple, right? It is straightforward. See,
Like I put
4.1,
but I
yeah.
did some bracket mistake.
All right, 4.141 minus 37 kilo into 11.3 micro.
Is it 3.71 volts, sir?
Yes, it is 3.71. Who is that? Naman.
Naman.
Okay, yeah. Okay, yeah. 3.71 volts. Yes. So others, please check. Okay. Now next is VC. So how will I write VC? Let me check with Bhavana. Bhavana? Bhavana, are you there?
Yes, sir.
Yeah, Bhavana, tell me what is VC?
VC we can get by 20 minus 6.8K into
Very good. I into IC, right?
IC. Yes, sir.
Yeah. Yeah. So what is VC value?
Yes, sir, I'm doing.
Okay. Let me check with Pradyumna. Pradyumna?
10.7452.
Yeah, it is 10.745. Thank you, Pradyumna. Naveen.
Yes, sir.
Yeah, Naveen, so far we did actually DC analysis. We evaluated the operating point. That means we know all the currents. We know the terminal currents of BJT, and we also know the voltages at base, emitter, and collector. Right. Now, so this is the first step whenever you do an amplifier circuit analysis. The first step is DC analysis and see that the transistor is in active region. Now, by looking at the base and collector voltage, now let us evaluate emitter also. So, can you tell me, Naveen, what is VE, emitter voltage?
1 minute, sir. 1 minute. Sir.
Yeah. So you can directly find emitter voltage as 2.2K into the current, emitter current. Yes?
3.0074.
Yeah, right. So you can find in this way, or you can directly subtract 0.7 from your VB voltage, right? Because VB and VE, the difference is 0.7. So now you see your base emitter voltage. NPN transistor. So you have NPN transistor here. Base is at 3.7, emitter is at 3. That means emitter base junction is forward biased. Collector is at 10 and base is at 3. So collector base junction is actually at reverse bias, right? So transistor is in active region of operation. Is that clear, Naveen?
Yes, sir.
Okay. Okay. Can you just tell me what is next step?
I have to find input impedance.
Yeah, we have to find all the other things. So what I'll do is I will start. So first heading what I wrote is DC analysis. This is the first step. Now I'll write the second step as AC analysis. That is a small signal analysis where I have to bring in the small signal equivalent circuit. Okay. Okay, Naveen. Nishant.
Yes, sir.
Yeah, so Nishant, before I draw the small signal equivalent circuit, I can actually find few parameters and get ready for the calculations. Can you tell me which are all those parameters?
Sir, I need GM.
Yes.
GM is IC by VT.
Yes.
I need R pi.
Okay, what is R pi?
VT by IB.
Okay.
And RE will be R pi divided by beta plus 1.
Very good. Very good. Okay. So thank you, Nishant. Now let me check with Nitin. Nitin, are you there? Nitin?
Sir?
Yeah. Nitin, can you tell me what is the GM value? One more thing I'll say here, GM is actually equal to 1 by RE, right? It is actually alpha by RE, or it can be taken approximately equal to 1 by RE. Okay. Can you tell me that? What is GM?
Yes, sir. 1 minute.
Yeah. Nitin, what is VT? VT in this? Hello, Nitin.
26 millivolts.
Yeah. Okay. So with that, what is GM value?
Sir, I don't have my calculator with me, so I'm
Okay.
having
Okay.
control.
Fine. Karthik?
Yes, sir. It's
Yeah.
coming out to be 0.0523. Simon.
0.052?
3 Simon.
Okay. So can I write it as 52.3 milliamps per volt?
Yeah.
Okay. Very good.
Sir, one doubt can I ask?
Yeah. Yes, please.
I had a doubt that those capacitors in the amplifier circuits, right?
Okay. Yeah.
Still didn't get what's their role in like this. Like, do they affect the amplification or anything? Like, what
No.
exactly are they doing?
Yeah. I'll explain that. Now, so capacitors are, so say for example, if I'm not using capacitor, especially at the input and output side, if I'm not using the capacitor, and you will be connecting actually a source directly to this point. Right. Now, we know that for a transistor or for a circuit to act as an amplifier, we should properly bias it. We should make sure that the biasing should be in active region. Now, if I'm not using capacitor, the current which is flowing here, so I say this is base current, but from 20 volts, there is one current coming here. Since there is a blocking capacitor here, since there is a capacitor here, this DC current is not flowing towards left, but it will find a path towards right and down. Right. Now, if this capacitor is not there, this current will actually split here, and a component will actually flow towards left through the source to the ground terminal. Now, what happens here? If an additional current is flowing here, additional in the sense from the 20 volt, if I'm getting another current, branch current here, this will definitely affect my operating point.
Oh, okay, sir. Yeah.
Right. Same is true even here, because I am connecting this output to some other circuit. If I'm not using a capacitor here, a current can actually flow towards this side.
Okay, it'll affect the biasing.
Yeah. So basically, all the capacitors are kept actually to make sure that the transistors are in the proper operating point.
Right. So the DC current is contained within that, and it helps in.
Yes. Right. Yeah.
Oh, okay. All right. Thank you, sir.
Yeah. Thank you. So we are with Karthik, right? Hello, Karthik.
Yeah. Yes, sir.
Yeah, Karthik. Yeah, go. Oh, you only asked the doubt, right?
Yeah.
Okay. So Karthik, can you tell me so you told me the GM value.
Yeah. GM.
Okay. Thank you, Karthik. Kiran Kumar.
Yes, sir.
Yeah. What is this R pi? It is VT by IB.
Just a sec.
Yeah. Or we know that this beta plus 1 into RE. So any form you can find. What is the beta value? 121.
So is it 2.29K?
Yes, it is coming around 2.28 kilo or something. Yes, correct. Thank you, Kiran. Yeah, so that is R pi. Now, Charan Kumar.
Yes, sir.
Charan, what is next step?
Sir, finding RE.
RE, yeah, anyway from R pi we will get RE, or if you are representing it as R pi, then RE is not required.
Voltage gain, sir.
Yeah, voltage gain. For that, what I need? Small signal equivalent circuit, right?
Yes, sir.
Yeah, so I'll draw the equivalent circuit of transistor now. So it is GM V pi. This is R pi. This is for transistor. Charan, whether early effect should be considered here?
Sir?
Early effect.
No, I think, sir.
Why? So how do I know whether early effect should be considered or not? How do we know? So this is a question given. Yes, Sharon, any answer?
No, sir, I don't know.
Okay, Sharon, yeah, I'll come back. Pallavi?
Yes, sir.
Yeah, Pallavi, whether early effect to be considered?
It should not be considered, sir.
Why?
The early voltage is not given in the
But
question.
something else is given in the question. Yes, Pallavi. Any idea?
No, sir.
Okay, Ashwit.
Yes, sir.
Yeah, can you help me in finding whether early effect should be considered or not? Ashwit?
Sir, I don't know, sir.
Okay, Renuka. Renuka?
Yes, sir.
Yeah, can you tell me, Renuka, whether early effect should be considered?
Yes, sir.
Why?
R naught is given.
Okay, very good. Yes, since R naught is given, I have to add R naught here in the model, right? Okay, Renuka. So now the question is to Harshita.
Yes, sir.
Tell me, Harshita, how will I complete this equivalent circuit?
So come again, sir. I didn't get you. Sorry.
No, how will I complete this equivalent circuit?
So you need to draw or not.
R naught is there.
No.
R naught is there. R naught, I think the value of R naught is 50K.
Yes, sir.
Yeah. Now, can you tell me what are the other components to be added?
Sir, those resistances.
Yeah. Tell me which all resistance I should add.
So that 80, 180K and 47K resistances. Those two are in parallel, right? We need to.
Yes.
We need to keep them at the base side.
That means here.
Yes, sir.
From here to which point?
So can you show the question once?
You do not have question with you.
No, sir. I didn't copy it actually. I just
Okay.
want to
Okay.
have it. So maybe to the graph. I'm not sure.
Maybe. Why?
I'm not sure.
Okay. Tell me why that the clarity is not there.
No, sir.
All right. I'll
Actually,
check.
I didn't follow. I'm not following these questions. So for previous two questions, I was there, but I didn't write this question. So.
Okay, Praveen. Praveen, are you there?
Yes, sir. Yes, sir.
Yeah, Praveen, can you tell me what to be done now?
So, will you tell the question, sir?
Oh, so you are not listening to me?
Sir, I am listening, sir.
Okay, now what to be done next? So this is the equivalent circuit what I have now. So what to be
Yes,
done
sir.
now?
Sir, we should connect RE, sir.
RE.
Yes, sir. Emitter resistor, sir.
Okay. All right. So Rajat?
Yes, sir.
Yeah, Rajat, any idea what to be done now?
We need to find Z out. So RC
Okay.
or not.
Okay, Rajat. 1 second. Okay, Rajat. Yeah. So now I'll explain what to do now. So we have drawn the equivalent circuit of the BJT. Now you can see that at the base there are two resistance. Now 180K is connected to 20 and 47 is connected to ground. But we know that for AC this 20 volt or this DC supply will act as ground. So 180 and 47K both are in parallel from base to ground. So I'll add a resistance here, and that value is 180K parallel to 180K parallel to 47K, which is 37. This is 37K, and this is the point where you are applying the input. So at AC, at the assumption here is for AC analysis, the capacitors acting as short. Right. Now, looking at the emitter, there is a resistance connected, but since there is a capacitor and capacitor is acting as short, the emitter point need not to be disconnected. This resistance need not to be connected. I can directly ground that point. Right. And now looking at the collector side, there is this capacitor also act as short. So from here we'll take output. Again, there is 6.8K resistance connected from collector to 20 volt, which is again ground. So this is V out. And here I have the 20, what is the resistance value? 6.8K. So this is 6.8K resistance. Right. Now we know this is a common emitter amplifier. So the voltage gain expression AV is equal to, can anyone of you unmute and tell me what is the gain expression for this?
Minus GM R0 parallel RC.
Yeah, it is minus GM into R0 parallel to RC. Now you can see that this is V pi, this is V pi, and this is Vin. Since these two are in parallel, your V pi is same as Vin. So since your V pi is equal to Vin, the gain expression also remains same. So you can evaluate this value. You can evaluate the. Can you tell me the final answer for this voltage gain?
So is it minus 313.363?
Any other answers? Yeah, it is 31. Any other answers?
Minus 315.8.
Yeah, it is minus 315. Yes, minus 315.88. Yeah, 313 is also right. So whatever you get within range of 310 to 315 or 320 should be fine. So this is AV. Now what are the other two parameters we need to find? We need to find Zin and Zout, input impedance and output impedance, right? So input impedance is the impedance seen from this point. So this is Zin, and output impedance is the impedance seen from this point. This is Zout, right? So who can tell me what is Zin? Subramanian. Yeah.
So R pi parallel 37.26.
Very good. R pi parallel to 37 that change. So what is the value?
So 1 second.
Yeah. All right.
2.6
You will
kilo.
get 2.16 kilo. That is Zin.
I mean 2.16.
Yeah. And Zout is directly 50K parallel to 6.8K, and that is equal to 5.986
kilo.
Yes. Very good. Yeah. So that is how we evaluate this question. We evaluated RE. RE is nothing but 1 by GM or alpha, 1 by GM, Zin, Zout, and AV, right? So if you have, yes, 1 second.
Okay, sir.